Thanks first to the organizers for inviting me. I'm very happy to be here. So my talk is going to be about collapse models, which for those who went to Angelo's seminars last week or the week before, they'll know all about them. They're basically a means of solving the measurement problem by having the collapse of the wave function encoded in the dynamics explicitly. And what I want to do is think about how first, whether collapse models can be made consistent with what we know about space-time symmetries, and how that might influence our thinking about collapse models. By space-time symmetries, what I mean here is, well, I'm actually just grouping together two things which I find interesting. The first is the principle of relativity and the associated Lorentz symmetry, and the second is time reversal symmetry. Now, the first of these is probably going to be considered a prerequisite for any theory to be taken seriously. The second, time reversal symmetry, less so, but I think it's something that perhaps we should be concerned with, given that dynamical laws, as far as we know, are time reversal symmetric. With the pertinent example, perhaps, of wave function collapse. And so what I want to argue is that taking into account these space-time symmetries actually forces us to completely rethink our view of collapse models. And collapse models, typically what you do is you start with the wave function, you include in the wave function dynamics some explicit collapse process. But I think the inclusion of space-time symmetries into the equations leads to a picture which is primarily concerned with actually just matter, definite matter distribution in space and time. And that you should really think of the wave function as actually the probability distribution for where, how future matter is distributed, conditional on what the past distribution matter was. So this is in no way changing the mathematical structure of collapse models. It's just a new view that I want to try and promote. So this is the outline of my talk. First of all, I'll briefly say what are collapse models, and I'll give my own special take on that. And that'll be just for the purpose of sort of seeing where we're heading with this. I'm then going to go and talk about the general structure of collapse models. So what is the the generic mathematical structure that underlies most of the well-known collapse models that are taken seriously? And what essentially that is, it's a modification of the Schrödinger dynamics that leads to some objective collapse process. I'm then going to argue that actually you can view the collapse process as an inference. So you can, rather than thinking of the collapse as some physical process which affects the wave function, I can think of it more as an updating of the wave function on the basis of some information acquired. I'm then going to show that, or rather just show a result, that in terms of the distribution of matter, collapse models can be taken as time symmetric. So this is perhaps a little bit counterintuitive, given that the wave function dynamics is time asymmetric. Then I'm going to talk about how we can incorporate relativity into this structure. And the essential idea there is just that we want to find a way in which the probabilities for our distribution of matter can be defined in a Lorentz invariant way. The wave function, by contrast, if I think of an evolving sequence if I think of my wave function defined on hypersurface as a foliation of space-time, it's necessarily going to have some kind of foliation dependent, and that kind of seems unnatural. But in terms of the actual distribution of matter, things look much better. And at the end, I'm going to just briefly mention gravity and how this picture can perhaps lead to some a different view of whether we can actually combine quantum matter with classical gravity. So the first bit, what are collapse models? So typically what you do is you start with a wave function described by the Schrödinger equation. Then you include some additional stochastic nonlinear dynamics, which will hopefully give you a description that will, if you have then a measurement situation, something which is unambiguously a measurement situation, it will describe the collapse of the wave function. On the other hand, if you have something which just looks like a system of a few particles that you'd expect to just satisfy the Schrödinger equation, then this new modified dynamics should just give you a good approximation to that Schrödinger dynamics for that small system. Finally, what you do is you take this wave function description, and from that you try to get some description in terms of local properties, definite local properties in space-time. So this is typically called primitive ontology, and it's often overlooked in collapse models. And what it is, it's a way of making sense of the collapsing, or taking the collapsing wave function and turning it into something which corresponds to our everyday experience of the world. So there are a couple of different ways to actually get a primitive ontology from wave function collapse dynamics, which I'll talk about at the appropriate moment. But at the end of the day, what you end up with is something which looks like a distribution of matter in space-time. And so the novel kind of view I want to bring to this is that it's a bit in bold, actually. So collapse models describe the distribution of matter in space and time, ultimately, as I just explained, but it is legitimate to regard this as the starting point. In other words, there is just matter in space-time. How best to describe it? So the idea is that there's just matter there, and the role of the wave function is actually to determine how that matter is distributed. So the role of the wave function is to determine the chance of a given matter distribution in the future, conditional on the matter distribution in the past. The physical collapse of the wave function can be viewed as a Bayesian updating based on new matter density information. And just to kind of give you a visual picture of what I mean by that, and this is just a simple example where I've got some matter density. Red means high, yellow means low. So this is just an object moving with uniform velocity to the right-hand side. What I've got in the second cell here is I've just taken a dense sample of points of that distribution. So these are Poisson distributed set of points. And then finally in this cell, I've just added a bit of Gaussian noise to the actual values of matter density. So you can see you kind of have the same general picture, but what I want to try and convince you is that this is actually the natural primitive ontology for a discrete version of the CSL model, which is one of the most, it's regarded as one of the best candidate collapse models. So for all the variation in different suggested collapse models, I would argue that there is a common underlying structure, common underlying mathematical structure, and it looks like this. Against a background of unitary dynamics, you have occasional collapses occur. So your state will just be evolving unitarily, and then at some time, and these times, they may be distributed regularly or or they may be randomly. But when you encounter one of these times, the state ceases for an instant to satisfy these unitary dynamics and instead undergoes the action of this collapse operator or jump operator. So that's dependent on some classical variable, Z. Z is a random variable. And Z actually has this probability distribution. And in order for this to be a well-defined probability distribution, then this the J operators must satisfy this completeness relation. So I've assumed here that it's self-adjoint. So those familiar with generalized quantum measurements will realize that this mathematically is identical in terms of its effect on the wave function to as though you were performing a generalized quantum measurement on the wave function at this time t. And J there corresponds to the measurement operator. So the difference in philosophy is that this is assumed to occur spontaneously rather than in response to an actual measurement. And so an actual collapse model is just corresponds to a sequence of these jumps occurring on the wave function. So it's mathematically equivalent to a random sequence of generalized quantum measurements. And so this is a discrete picture. Continuous collapse models can be explained by taking a kind of limit case of this particular construction. But I think this gives a nice kind of physical picture of what collapse models are actually doing. So a specific example of a collapse model then just corresponds to a particular choice of what the J operator is and a particular choice of what the sequence of times at which these collapses occur are. So here's a couple of examples. The GRW model, the collapse operators just correspond to these projections onto, they're essentially like weak, this is essentially like a weak measurement of what the position variable of a particle is. So the collapse events are just sprinkled uniformly in time. And so what you have is that when this collapse operator acts on the wave function, it's going to narrow the amplitude of the position variable about this random position Z, which of course is chosen by this probability. So these jump operators happen independently to every single particle in the system, and are independent Poisson distributed random times. And you might ask, well, if these collapses are just happening randomly, why is it that I only see collapse occur when I do an actual measurement? Well, the reason is that when you do a measurement, what you're doing is you're coupling your you're entangling the state of one particle with the state of a whole bunch of particles in your measuring device. And it only takes, typically, if the whole measuring device points one way, it only takes one of those particles to actually collapse to cause the collapse of the whole entangled system. So you can have the actual rate of collapses per particle can be so small that an individual system is rarely an individual particle is rarely affected. But once you set up a quantum measurement situation, you're going to rapidly get collapse. So the second example is the CSL model. So the CSL model is typically a continuous model, but this is a kind of discrete version of it. Now what you've got are the collapse events are sprinkled uniformly in space-time. And these are equivalent to weak measurements of the number density of particles at a particular position. So if this is the point in space-time where this collapse operator has been sprinkled, then it happens at the component time t, and it leads to a weak measurement of the number density of particles at the component spatial coordinate. So what you've got in both of these cases are, in the first example, you've got this operator is effectively making lots of random measurements of where the particles are. And this operator is making lots of random measurements of what the number density is, or the number density of particles is, all over space-time. So when you add together all these sets of collapse outcomes, so these are the Zs are effectively the measurement results. When you bring them all together, what you have is effectively a description of the distribution of matter in space and time. So the point then is that I want to then regard this, I want to kind of change my view of, in this whole construction, what you see is then, well, let me put it this way. So given that this actually gives a distribution, this represents a distribution of matter in space and time, why not I regard that as actually the distribution of matter in space and time? So this is commonly called the flash ontology in the context of the GRW model, because what these Z values are effectively flashes just telling you where the particles are positioned in space and time. So there's also something called the matter density ontology, which is where you kind of take an expectation of a particular operator. Just for those who know that, and that's not what I'm concerned with. And when I'm talking about Zs representing the distribution of matter, I'm particularly, what I mean in particular is these kind of collapse outcomes. So it kind of makes sense now to just call them the collapse outcomes, or even the distribution. I'm just going to call these Zs the distribution of matter. So you kind of see in this construction that it's kind of what we've ended up with is a distribution of matter to describe the world, but it's kind of a byproduct of this whole kind of collapse dynamics. What I want to try and sort of argue is that maybe we should just take that matter distribution as primitive and see if we can think of a way to explain this whole thing without this being a kind of, without it being so intertwined with the wave function. And so on the next slide, let me try and do that. So first of all, what I'm going to regard these collapse outcomes as some noise, as a signal component plus some Gaussian noise. So what I'm doing here is that in this variable A, I'm trying to capture the mean value of what this Z is. I'm assuming it's stochastically varying. This noise term is going to give me the stochastic variation. This is going to be the mean value. I'm interested in trying to describe the mean value of it. So, well, I'm just saying that I kind of you kind of see some stochastic variation in the realized values of Z. I'm just going to try and strip that away for the purpose of modeling it and try and calculate some mean trajectory. Okay. So I first of all assume that the probability distribution for this A variable is given by this. So this is where the quantum behavior enters. So this is really just a C number variable, but I'm just going to assume that it has this funny probability distribution. So So what I would do is first of all find some operator A hat to represent A. I'd find the eigenstates of A hat, and then this gives me the probability of what the particular value of A is. So this is a perfectly valid probability distribution. There's no real funny business going on here. But like I said, this is where the quantum behavior enters. And then given this probability distribution for A, I then want to ask, well, suppose I'm privy to a new value of Z. I acquire some value of Z. After all, I'm assuming that this actually is this is actually what I'm experiencing as matter distribution in the world. So I then want to update my distribution of A on the basis of that information. So I just use Bayes' rule to do that. But it turns out that, and I'll spare you the details, which are straightforward in any case, but this formula is actually equivalent to as though the wave function had undergone the action of this particular projection operator. So in other words, there's a mathematical equivalence between the idea of the state undergoing the action of this collapse operator and the acquisition of some noisy information about some underlying variable. So in this schema, also the probability of the particular value of Z is exactly the same as it was in the usual collapse model framework. So what I want to argue with this last slide is that the collapse process is mathematically equivalent to a Bayesian updating on the basis of noisy information. That noisy information being the specific collapse outcomes which we're taking to represent the actual matter distribution of our experience. The role of the wave function is in determining the probability of this mean variable A along with its dynamics. So A, as I said, it represents some mean value of the signal part of the matter distribution stripped of noise. So, okay then, imagine that you have, in the GRW context, you just have a particle trajectory. Now the collapses are going to appear as point-like events along that trajectory. So what I can do is strip away the noise, so try to come up with an average value of the trajectory. That would be what the A was. In the context of GRW, if you were going to take it to be the CSL model, the A would represent the number density distributed over space-time. Okay, so the next point I want to make is about time symmetry. So wave function collapse is typically assumed to be a time asymmetric process. But now consider this. I've got an entire timeline of the universe. I've got some initial condition, which I've now generalized to a density matrix state. And I actually impose a future condition. What that isn't, it's not saying that the state has to be precisely of that particular form at the end of time. This is more like kind of a POVM constraint on the state at that time. Then what I have is just my sequence of collapse outcomes throughout the whole of time, separated by these particular time intervals. So these are what I'm taking to actually represent the distribution of matter in the course of the universe. So then using the standard collapse model dynamics, I can reasonably ask, what's the probability for this particular sequence? And what you find is that the probability of this ordered sequence is exactly the same as the probability of the sequence in the opposite order, with the time intervals all in the opposite order, and the future condition and the initial condition swapped. And that is true whenever you can find some basis such that the jump operator and the unitary operator satisfy those requirements. So rho star here is that means conjugation within that particular basis. Yeah. Well, these are unitary development interspersed with collapses. But the question I've asked here is just what is the probability of the particular collapse outcome values? I should add this, okay? So first of all, I've imposed a future and past condition. So any asymmetries that sort of physical asymmetries that I observe in that kind of behavior must be due to the asymmetries of the boundary conditions, because what this is showing is just at the level of the actual outcomes. This was our experience of what is going on in the world according to this particular collapse model framework. There's no way to determine from the probability what the order is. So this probably just repeats that. This means that the collapse dynamics can be applied in either time direction. We arrive at the same probability for a given complete set of collapse outcomes. So at the level of the collapse outcomes, there is a structural time symmetry. So this might seem a bit counterintuitive, given that we're used to thinking of the collapse of the wave function as an asymmetric process. But indeed, in terms of the wave function, the description is time asymmetric because, in this view that I'm trying to promote, the wave function is a means of conditioning on the past collapse outcomes. So the wave function at a given time is the result of conditioning on every single noisy information that I've got from the matter distribution. So I could equally well come up with a wave function that was describing backwards in time evolution by conditioning on all future possible collapses for the purpose of estimating what matter was in the past. So, yeah, and let me just reiterate, that any actual observed asymmetries that we can see, for example, in a collapse model, you'd expect some kind of heating, then that kind of energy increase is clearly time asymmetric. That has to be squarely put down to the fact that I've got asymmetric boundary conditions. So now let me talk about relativity. So in order to have this model satisfy the constraints of relativity, what I want is, at the phenomenal level, I want Lorentz invariance, and I'd also want that I don't have any dependence on a particular frame or foliation. So as a first step to doing that, I want to get rid of the particular time slicing that I was using before and be able to advance from an arbitrary hypersurface to another arbitrary hypersurface to the future of that one. And the way to do that is to move to the Tomonaga picture, or the interaction picture. And there you just, in the non-collapse view, at least, you just replace the unitary operator with this one where that's the interaction Hamiltonian. So this kind of preserves the sort of physical picture that we had before. And in order to then include collapse events, what you do is you just sprinkle them with a Poisson distribution in space-time. So if they're distributed with a Poisson distribution in space-time, that means that they would have the same distribution if I look from a boosted frame. So the construction is Lorentz invariant. And associated to each one of those points, I just have a jump. So just as before, the state ceases for an instant to satisfy the Schrödinger equation and instead undergoes this jump. And the probability of the particular collapse outcome has the usual formula and the same completeness relation. So again, it's just like a generalized quantum measurement occurring in terms of, it's equivalent to that in terms of its effect on the wave. So there's something else I need to do, which is I need to impose this set of constraints. So the interaction Hamiltonian has to commute for space-like separated points, and collapse operators have to commute at space-like separated points, and the collapse operator and the interaction Hamiltonian have to commute at space-like separated points. The reason for that is that if I'm thinking of advancing the foliation first through point X and then through point Y, I don't want there to be any physical consequences of that ordering. They need to give me the same result in both cases. More generally, this leads to the foliation independence. You can actually show that for a given set of collapse outcomes, for all collapse events at these locations between two hypersurfaces, then this state is unambiguously determined. Sorry, unambiguously determined from the initial state, independently of the foliation to get from sigma to sigma prime. And furthermore, you can show that the probability of the set of collapse outcomes occurring at these particular positions is independent of the foliation. So finally, if these are Lorentz, if these are scalar operators, then the probability assigned to some set of collapse outcomes or some set of matter distribution in the future is Lorentz invariant. So again, it makes more sense to treat the collapse outcomes as primitive and the quantum state as derivative. Why? Well, assuming that the collapse outcomes provide an empirically adequate picture, this results in Lorentz invariance at the phenomenal level, in which the underlying processes do not use a preferred frame. By contrast, a state history is necessarily foliation dependent. So in order to provide a state history, I need to take a particular foliation. But in terms of the picture I'm trying to promote, this is actually a natural consequence of its interpretation as a state of information about past collapses and the need, in that case, to demarcate past-future boundary for this purpose. So the actual foliation dependence of a particular state history is actually quite a natural feature of this kind of view. And incidentally, I mean, you can different sets of state histories defined on different foliations will be consistent for the simple fact that the set of collapse outcomes, they will be consistent about the set of collapse outcomes. So here's a particular example. I just choose the collapse operator as effectively as analogous to a weak measurement of this kind of mass term of a complex scalar field. So what this would be doing is just this, the Z values would be essentially measurements of, equivalent to measurements of this particular variable. But the problem is that So first of all, this can be shown to reduce to the CSL model, but without smearing of the number density operator. Now that is actually a bit of a problem, because this then, what this does, it causes sharp discontinuities of the field state whenever it acts. And that leads to infinite energy density increase, which is a bit of a problem, let's say. I just want to say that a possible resolution of this is just regulation by discrete spacetime. This would provide an effective smearing for this particular operator. So let me just kind of end with a few remarks about what this whole view might have to say about gravity. So the problem we have is that how to make sense of Einstein equation, given that this is an operator and this is a C number valued tensor. So usually, I mean, the general consensus is that we should be thinking about quantizing gravity, but given this view of taking the kind of the distribution of matter as the sort of primitive aspect of this model of collapse, it kind of makes sense then to determine what the energy momentum tensor is from the actual realized definite distribution of matter. And this idea has been used in the Newtonian case in this particular example, and I think the result is has a surprising mathematical elegance. So I just want to see how this idea can undermine some no-go theorems for how we combine quantum matter and classical gravity. For example, these two by Epley and Hanna. So the first one concerns cases where gravitational waves can interact with quantum matter without causing them to collapse. So what you do then is this is a kind of simplified version which captures the essential idea. You take a particle and you place it in a superposition of two different locations, each in its own box. Then what you do is you monitor one of those boxes by scattering gravitational waves off it. If that doesn't affect, if that doesn't cause a collapse, that is somehow giving you some information that the state is in a superposition. Then what I do is I perform a measurement on here. That gives me an instantaneous change, which I might be able to observe from the scattered gravitational waves. So therefore, I can communicate faster than the speed of light. The reason why it doesn't work in this matter distribution view is because in order for the matter here to have an effect on gravity, there must be collapses. And you can actually just use the no signaling theorem to show that any measurement I make here has no statistical influences on the collapses that are happening here, using the fact that they are mathematically equivalent to generalized quantum measurements. Since I'm running short of time, I'll skip the second one, but it's equally straightforward in terms of how it resolves that particular paradox. But there is one problem, which is that this is the kind of standout problem, which is that the Einstein tensor is conserved because this is the contracted Bianchi identity, but typically the energy momentum tensor, if I'm describing it in terms of collapses, is not going to be conserved for a number of reasons. First, if a collapse, the action of a collapse is to localize the state, then that is instantaneously going to lead to spreads in momentum. So that's going to lead to non-conservation of energy. Also, the simple fact that a collapse in a kind of measurement situation chooses one particular outcome over another is going to lead to non-conservation type situations. So you need to somehow resolve this inconsistency. And the only thing I want to say with respect to that is that this problem might also be resolved by having a discrete spacetime, because you can take, for example, regicalculus. Okay, I'll just do one more minute. What you find in regicalculus is that, which is a picture of discrete spacetime geometry, is that this is only actually true in the case where spacetime becomes smooth. So it actually offers an opportunity to recover some kind of consistency. So that's my conclusions. So I'll quickly read through. Collapse models describe definite valued matter distribution in space and time. So this is my kind of the view that I'm trying to promote in this talk. The wave function can be understood as representing a probability distribution for how matter in the future is distributed given the distribution of matter in the past. Collapse can be understood as Bayesian inference. So let me just make one more statement about these two. This is actually objectively defined given the process. There's no subjectivity in the wave function. The distribution of matter is structurally time symmetric. Probability of a given distribution of matter is Lorentz invariant and independent of space-time foliation, and hints at a discrete space-time structure. So, thank you.
Sir, what is the implication of time reversal symmetry on the second law of thermodynamics?
Well, one implication of this particular result is that for anyone who is attempting to try and explain the second law through the time asymmetry of collapse models, then you're wasting your time, I think, because I think this argument demonstrates that that the dynamical process is actually time symmetric, and asymmetries have exactly the same, require exactly the same kind of explanation in terms of initial conditions.
How does it help in establishing the second law of thermodynamics?
No, because I mean the wave function is just kind of, I would argue it's just a useful intermediary tool for the purpose of predicting the matter distribution. The matter distribution is what is the ontology, and that is our actual experience.
Point. You well know that for a given density, mass density distribution can have different wave functions that project the same mass density distribution. So in which sense the wave function is just the law? If you don't specify the initial wave function, you cannot describe the future.
Yeah, you have to have an initial constraint. But once you have an initial constraint, it's objectively defined, because it's provided you update with every single collapse outcome, or every single value of the matter distribution throughout the whole of history.
Yeah, but okay.
Equivalent.
But I think, okay, I sense it weakens this nomenological interpretation of the wave function thing. No.
Which constraint? Yeah.
It's an initial wave function, initial constraint.
Yeah. Okay, yeah. So it's an initial probability distribution, an initial objective probability distribution for what the future matter will be. Well, I mean, there are, okay, that might be you might be having to add an additional part to the, yeah, but it may be the way that you can get around that, in the sense that there are some results on lattice model of collapse which show that given a set of matter distribution, a set of collapse outcomes, you can start with many different wave functions. And that once they evolve through that set of collapses, they all tend to the same wave function. So it may be that what you're talking about just get washed out. You can consider it as an estimate of the probability distribution.
I think you can deal the problem the same way they deal it in Bowe mechanics, I suppose, that you have to consider the wave function of the universe as the law. So that's it. But then you have to prove then that for subsystems you have effectively the collapse models as we know them. So I think you can solve this problem, and you have to consider the wave function of the universe. And then you have to prove with some argument that if you restrict to a subset of the universe, then you have the models as we know them, which has been done somehow in Bowe mechanics for that. Perhaps, I mean, work and comment on that.
So, I'm not sure. Sorry? But what the ontology is?
The question is whether you require, you can't demote the wave function so much as I have been saying, that you require it to describe what your initial condition is.
So part of the ontology is the wave function at an initial time too, right?
Yeah.
Oh, yeah, okay. But you could say the same thing in Bowe mechanics.
Okay, but it plays a role in part of the ontology. The ontology is not just the matter distribution.
Yeah, yeah. It plays a part in the theory. In the end, you can say maybe it's more like Angelo was saying. It is still there in the theory, if you want to call it ontology or part of the law.
I have another small question, which is very interesting. So you said the fact that we have self-heating by the collapse theory is due to initial and final constraints. How would I set up initial and final constraints so that instead of heating, I would have cooling?
Just the opposite to what they are now.
So give me an example.
You just have no constraint on the initial condition of the universe, and at the end of the universe, you have a Big Bang initial condition, the equivalent of Big Bang.
Big crunch.
Big crunch.
Hi, thanks very much for the talk. Did I understand right? You said your Lorentz invariant construction, you sprinkle points in space-time through a Poisson distribution?
Yeah.
I don't know what that means when a Poisson distribution on Minkowski space. Can you elaborate?
Just if I take an incremental space-time volume, there is a fixed incremental probability that there will be a collapse event associated at that point. Just in the same way as a Poisson distribution in time is, I have within a fixed incremental period of time, there's a fixed incremental probability that.
Yeah, are you sure there's a Lorentz invariant way of doing that incrementation and defining the distribution?
Sorry?
Are you sure there's a Lorentz invariant way?
This is what they do in causal set theory.
Well, let's discuss offline. Okay, but thank you.